So today's speaker is Dr. John Notte from Carl Zeiss. In addition, he does have two of his colleagues here, Dave Voci and Brian Majak. Am I pronouncing that correctly?
Sure.
Okay.
Thank you.
Back there. But John is the speaker, so I'll give you his credentials. John received his bachelor's degree from Case Western and his PhD from Berkeley, UC Berkeley, both in physics. And then he moved to Bates College, where he taught physics, astronomy, and math, while developing electron traps as a follow-up to his doctoral research. After leaving academia, and why anyone would ever want to do that, I have no idea, John has been at several different imaging companies, including Amray, KLA-Tencor, and FEI, where he worked on electron optics, detector optimization, and system automation and image analysis. He first began working on the helium-ion source when he started at ALS Corporation in 2005, and he has continued this in his current position as Director of Research and Development at Carl Zeiss. And today he is going to give us an introduction to the helium-ion microscope.
Thank you very much. Thank you. So I will give an introduction to the Orion helium-ion microscope. This is a technology that's really in its infancy, and we're very excited to see it take its first steps and kind of grow, and people finding new and exciting things to do with it. I also want to subtitle this talk because the helium ion just happens to be ideal for these purposes. There are electron microscopes, an awful lot of them, and they're well established with a long, proud history. There's also gallium microscopes, or gallium-focused ion beams. They also have very valuable purposes. But between the mass of the electron and the mass of gallium, there's actually a very interesting intermediate mass, and that's where helium happens to be at. So aside from the fact that helium is a terrific atom to work with, it's also got just the right mass, because a lot of things wouldn't work nearly as well. So here's a nice logarithmic scale, and let me just show you this graphic at the beginning. That's the mass of the electron. Here is the mass of gallium. This is the whole periodic table up here. Gallium is around here, and helium is somewhere in the middle. It's kind of like the Goldilocks story. It's just right. Photons way down at this end have no mass, and the problem with them is they have diffraction. They're too wave-like. And that's really the problem with electrons. As light as they are, they still exhibit a lot of wave-like properties. And that means when you pass them through a slit or a small aperture, they tend to diffract. And that limits the ultimate probe size you can get with an electron microscope. It's one of the biggest technical challenges why the electron microscope makes improvements, but relatively slow, because they're dealing with the wave-like properties of the electron. So let me jump down and just give a little bit of history. I am indeed a physics major, but when I was undergraduate, I also decided to get a second major in history of science and technology, which is a field that's really dear to me, and I understand it a lot better now, actually having been involved with a technology that's newborn. This is the fellow who really gave birth to this. His name's Erwin Muller, and back around 55 years ago, he developed something called the field ion microscope, and I'll talk about that in just a second. Following that, a bunch of people realized, hey, this is a really neat technology. Maybe we can make a gas field ion microscope, or GFIM, out of it. And these are a lot of the pioneers of gallium and SEMS and other terrific innovators of this field in the last 50 years. And they worked very hard. They did a lot of excellent work. A lot of people optimized this technology, but still it wasn't quite ready for commercial prime time. Now, sometime a decade or two later, around 1985, the advent of the gallium liquid metal ion source started to work, and started to work well. Now, that was actually a deterrent. That actually retarded the advance of the gas field ion microscope for a long time, because people were quite happy because there was something to fill the void. There was some sputtering ion beam that they could use. So work went slow. But with this gallium beam, there was actually a lot of neat stuff that happened. They made instruments like this that could perform mask repair and circuit edit. Terrific applications for the semiconductor industry. They could cross-section devices and then image them, getting great 3D information. But there was still some problem with gallium. And this is why the gas field ion microscope took off again. The gallium would contaminate the devices. And when that became a problem, Micreon got a good deal of funding from DARPA and the National Science Foundation, ORNL collaboration. And we got eventually around to making a proof of concept gas field ion microscope. And this is the instrument that was developed at Micreon Corporation about 10 to 15 years ago. And the idea of this one was to use a heavy gas, such as neon at the time, to sputter away materials. And this was thought to be fairly good. Micron was acquired by FEI Company, and they already had a good deal of gallium investment, and they eventually shut down that program, and they allowed us to take the intellectual property. They actually moved a lot of people out to Oregon. Those of us who didn't want to go formed this group of laggers who stayed back in Peabody, Massachusetts, and we took this technology with their permission and developed it into a product. And it wasn't long after until Carl Zeiss said, hey, this is a terrific product for not just microscopy, but manipulating the sample in various ways. So this gave birth to the gas field ion microscope, today known as Orion. So I just want to give you a little bit more history, because in learning about the SEM and its evolving over the last 60 some odd years, it's been really, really helpful. And these are some of the pioneers. I'll just flash them up one at a time. Ruska, back in the 30s, Manfred van Ardeen, the late 30s, Zworkin, this was the first US developer at RCA Labs, and Charles Oatley at Cambridge Labs. He did most of the last step work, him and his graduate students developing what are affectionately called SEM 1, SEM 2, and SEM 3. But if you notice the history here, it was not until 1965, a good 30 years after, that it really found its commercial application. So all this other time, there's a lot of fascinating explorations where they found it had different roles in different laboratories. It stayed in the lab for a while, but eventually it was not until the Canadian paper and pulp industry found that they could actually see 3D information better than they could in a TEM and better than an optical microscope. And that was when it really had its commercial success. And there's an interesting story by one of the folks who remembers, Bernie Breton, who's still at Cambridge. His recollection is the marketing experts, no offense, Brian and Dave, their experts said they expected no more than 6 to 10 SEMs would ever be sold. That would saturate the world market. And of course now there's, I think it's approaching 100,000 SEMs. It just goes to show you that there's tons of applications, and how fast we can learn them is really important. And that's one of the reasons that I'm here today, to let people know that there's this new technology, the helium ion microscope, and this new technology will have lots of different applications. And the faster we let everyone know about it, the earlier we'll start to discover these interesting applications. So let me move on now. This is what the microscope looks like, the commercial product, the Orion microscope. In the heart of it, the interesting physics part is in a column off to the side there. If we take it out and we break it apart bit by bit, it's comprised of a helium ion source at the very top. Below that is a first lens. This focuses the charged particles that come out. Beneath that is an aperture. This stops the beam to the desired probe size or amount of current. The scanning deflectors, we have a double deflection scanning system, and a final lens that focuses it onto the sample. So let's start at the top and talk about the source. This is really where all of the effort went to develop and make this a commercially viable project. It consists of a base which actually looks a lot like any other electron or ion source that you've seen. At the end is a very pointy needle. I'll show you some images at the very end, but it's atomically pointy. At the very end, there's a very small number of atoms in that last terminal shelf, not unlike an AFM tip. But this is a single crystal wire, so we know exactly how those atoms should be arranged. And if you could look at it in a powerful microscope, you'd see, yes, indeed, it's pointy. At higher magnification, you see it's got a radius of curvature to its end shape. And if it's made of a single crystal and is bounded by a sphere, you can imagine there's some very interesting structures that happen, because, of course, atoms are indivisible, but if it's a spherical shape, it actually has to have a faceted kind of end form. These are the atoms, if we could see them, on the tip. And this is the best atom-wise approximation to a sphere. Some of the atoms stick out more, some stick out a little bit less. And I've colorized them here. The ones that are yellow are the ones that stick out the most. The ones that are red don't have the same amount of sticking out. And I'm introducing the term sticking out. What I really mean is how big is the electric field at that atomic site. And you can see there's several of them that have huge electric fields. So if I put a voltage on this, let's say 20 kV positive, the interesting thing that happens is there'll be regions where I get electric fields as large as 3 or 4 volts per angstrom. That's about as big an electric field as you can get anywhere near matter. Beyond that, you actually start to rip the atoms off one by one. But just shy of that, that electric field in these little moon-shaped areas, what we call the ionization disks, is so big that if a helium neutral atom wanders into these disks, the electron will quantum mechanically tunnel out and go into the metallic crystal of the emitter. And the remaining ion, positively charged, sees the 30 keV on the bulk emitter and accelerates away. So each of those little ionization disks, once we flood in the helium, creates a little beamlet. So we get this collection of hundreds or thousands of little beamlets off of this tip. And this is why it was so important 50 years ago. This was the first time mankind had seen atoms. This was the first really strong validation that yes, indeed, we are seeing atoms. So you'd put a screen under here, a microchannel plate or a phosphor at the time, and if you take a look at that pattern, it looks like this. So this is the piecewise approximation to a spherical end form from a crystalline lattice of atoms. And each one of these little points is an atom on the tip. So right away you can tell these beamlets are originating from something the size of angstroms or perhaps even sub-angstroms. The ionization is happening at each of these sites, and so therefore one of the rules of electron optics is if you start with a very small source, you can actually focus it back down to a comparably sized probe size. So this means that we can get an atomic sized probe out of this technology, and this is why a lot of those researchers I mentioned earlier were pursuing it so vigorously. It was not really practical at this point. One of the big challenges was that with 1,000 little beamlets, they're all sharing the same helium gas supply. So the remaining challenge meant to either make it much sharper or find some way to make the field at just one atom. And the solution to that was to change the end form. But before I go, there's another one of Erwin Mueller's original device that he used. This was the first instrument that allowed mankind to see atoms. This is something you can hold in your hands. Remarkably simple, but it was very, very powerful at the time. Here's a picture of Erwin Mueller explaining it at the chalkboard. This was at Penn State, I believe. Here's a ghostly image of him looking at the first atoms. And here's his model that he had assembled of the tip. And this is exactly how he deduced that these were single crystal oral organized. Actually, to be honest, it was all his graduate student. So this is where all the interesting stuff happens. Of course, he got the credit and almost won a Nobel Prize for all this. But it was his graduate student, Badhar, who did all of the interesting work and actually suggested change the polarity. I think you'll see something amazing. And these are the atoms made up of the tip. And this is really a landmark moment in history of science. So here's the tip. There's the atoms on it. You get 1,000 beamlets. What we needed to do to make this commercially viable was to just change the end form into a vertex. We needed to induce some kind of faceting. And there's a lot of surface scientists out there who know about faceting and know that there's lowest energy states. If you play the right music, you can get the atoms to dance around, and when you turn off the music, they'll stop dancing and they'll leave themselves in these nice planar forms. So instead of a polyhedra of many facets, you can just get 3 facets, essentially a 3-sided pyramid at the end of this needle. Now when you turn on the electric field, you don't have a ton of these little ionization disks, you just get them at the terminal atoms, 3 of them for a 3-sided pyramid. And you just get a small number of beamlets coming out. Now of these beamlets, you can tilt these in and aim them down your column, and now you can use one of those to form a probe that can be quite commercially successful. Well, what we needed to do, really, to make this commercially successful was find a way to do that shaping process, that faceting process, and find a way to do it repeatedly. Most of our efforts that I worked on in the past years was really finding a way to get that rounded end form to change shapes until it's a perfect, atomically precise 3-sided pyramid, and then be able to go back to a rounded one, and then go back to the pyramid again. And you can, the way to go back is actually quite interesting. You just turn up your voltage a little bit more, and those atoms I mentioned will pop off at around 4 or 5 volts per angstrom. And they don't make popping sounds, but you can almost imagine them disappearing one by one until you get this rounded end form, where now the field is shared by hundreds of atoms. So here, like any ion source or electron source, there's a voltage-current relationship. On the horizontal axis is the extraction voltage that's applied. On the vertical axis is the emission current coming out of that trimer. We call it those 3 atoms. And you can see at too low a voltage, you don't get anything. Your pattern would look like this. As you increase the voltage, you start to see this trimer emission. You're starting to pull in more helium. The electric field sucks it in towards the tip and helps to ionize it. As you get closer and closer to the optimal operating voltage, they get brighter and brighter. Beyond that peak brightness, the operating condition we like to operate at, it actually starts to, the electric field gets big enough that the next shelf starts to turn on. And now you're starting to share your helium again. You're sharing it with more and more atoms, so each one of the ones you care about is less bright. As you go higher and higher, they actually get a little bit blurry, because the electric field is now ionizing off the surface of the atom. And as you go higher, even you start to pop off those atoms and you get this rounded end form. One of the neat things about this ion source is if you take a look at the beam current on the vertical axis and you take a look at the helium pressure on the horizontal axis, you'll find that it's perfectly linear. These are one at a time events. So if I want more current, I can add more helium. If I want less current, I can add less helium. So a leak valve actually lets you explore about 6 orders of magnitude in beam current. That's a dynamic range that's very hard to explore in a SEM or a gallium source. So of those 3 beamlets that are coming out, we tend to focus them through that first lens 1. They pass through an aperture that stops the other 2 beams. Yes, we're completely wasting 2/3 of our helium. And then the remaining part that comes down, we focus. We can also change the focus parameter so all of the beams go down. This gives you a bigger spot, but it gives you 3 times the current. Typically, for highest resolution, we send 1 atom's worth of helium beams down, like this. So that's the interesting physics, and believe me, there's an awful lot of people who've worked on that, and it's fascinating work. There's probably many more PhDs worth of interesting research in the source technology. But the real interesting stuff, where I think there's even more PhDs worth of research to happen, is in the sample interaction. What happens when a helium ion beam hits the sample? So I'm going to spend the rest of the talk talking about that, and then I'll talk about some of the applications that you can do based upon that. The probe forming, I mentioned, can be quite good. This is a common diagram if you're used to thinking about how a SEM can get its best probe size. The vertical axis is the spot size in nanometers. The horizontal axis is a semi-angle, or what you can achieve with a big aperture or a small aperture. This is the big aperture end. In a big aperture sizes, you're limited by spherical aberration. Make your aperture smaller, you're limited by chromatic. And then ultimately you get limited by diffraction, at least on a SEM you do, because it's a low mass, it's wave-like. So, but if we could drop that blue line by going to something more massive, like helium, this is the SEM, typical garden variety SEM, optimized at a couple of nanometers. Some of the better SEMs do better. But as we can drop our chromatic aberration, because we've got a smaller delta E over E, and we can drop diffraction because we've got so much more mass, now our best operating point gives us around 1/4 nanometer. So we're right around the size of an atom. We're able to focus that down the size of the ion source. But not only that, you'll notice that best optimal point is also at a smaller semi-angle. So we can get a better depth of focus than a SEM. So if you're looking at a tilted grid or a cross-section, you can get a lot of it in focus at the same time. Here's a nice crystal that was grown where you can see features in the foreground and background with a terrific depth of field. This is a good SEM image of some lines in a semiconductor device, but you can see with the Orion microscope, you can see that you get good focus not just in that first plane, but also further back. So if you need 3D information, it's actually turned out to be one of the features that people enjoy in using it, is that depth of field that you get. So I'm now going to talk about as that beam enters the sample, the interesting particles that are created. And this was largely explored. There's a lot of people who had studied it as part of the fusion program, because they have, after all, alpha particles, helium atoms, slamming into reactor vessel walls. And they had done a little bit of this research. But no one had really done the research for a focused probe of heliums. It just wasn't available. So if you could reveal and see what's going on under the surface, you see that the helium ion beam can get a couple of 100 nanometers down. And you can see there's a whole collection of particles that are generated here, some right at the surface, some deeper down, and I'm going to talk about them one at a time. But first I want to talk about that escape depth, or the depth at which the helium ions penetrate. I've got, in order of mass, I've got the electron beam being focused down, and as the electron beam enters a sample, it's an electron, and it's mostly interacting with other electrons. So they're the same mass. So like billiard balls, they tend to have wild scattering. It hits another object of the same mass and it can go off at any angle. So underneath the surface you see this large plume. A single scattering can make it come back. That's why there's such a large backscatter contribution to electron microscope images. A lot of backscatters, you'll notice some of those backscatters can exit way over here and they can produce secondary electrons. That limits the ultimate resolution you can get unless you do special filtering processes with an electron microscope image. The helium, being a little bit more massive, doesn't interact very well with the electrons. So as it goes in, it stays relatively collimated. And for reference, I've got what we call the secondary electron escape depth. It's a few nanometers for most materials. You'll notice the helium beam is still collimated over that length. So the electrons that are coming out of exactly where the beam went in. So you can get a sharper image. Gallium, on the far right, you'll see does something completely different. It interacts with the nuclei quite strongly, produces a lot of scattering. That's its primary purpose, that's its claim to fame. But what it does, it means that those recoiled atoms of whatever you're looking at are going to be bouncing around, and they can actually come out over here and produce secondary electrons. So if you want high resolution imaging, you want to get information right where you've parked your beam. Backscatters prevent you from doing that in the SEM, and some of the subsurface sputtering and recoils prevent you from doing that in gallium. So the helium really is a well-chosen mass for this microscope. Not to say that it couldn't happen for other masses, it just happens to work out quite nicely for us. So I mentioned that the subsurface scattering in an electron beam is a bit of an impediment. We call those SE2s that come out. And this is a nice simulation by David Joy at University of Tennessee, ORNL. This is what happens when you look at some aluminum posts on silicon with an electron beam. And you can almost imagine the beam is entering here and is creating kind of a glow under the surface. That's the backscatter volume. And you can generate electrons, secondary electrons, out from the neighborhood of where you park the beam. With helium, because it stays collimated in the material, you get secondary electrons right where you wanted to see them. So there's a nice contrast difference. You get different information, you get different depths of information, and different lateral information breadths. These are all the particles that can happen. They're secondary electrons I just mentioned. Those ones are typically 5 eV. They're actually lower energy distributions than you would find in a SEM, and that's important to some applications. The secondary electron yield ranges from about 3 to 8, much higher than a SEM. Every ion coming in produces a good handful of secondary electrons that come out. And you do get the secant alpha yield enhancement, so you get nice topographic information. Their escape depth is just nanometers, giving you the shallow information. There's also backscattered helium. The helium that went in, some fraction of them, typically a percent, sometimes a little less, sometimes a little more, some fraction of the helium that goes in will bounce out. That tells you some really interesting stuff. If you take a look at the scattering probability, the cross-section, it goes as the atomic number. So this gives you very good Z contrast. I'll show you an image of that a little bit later. But also you can take a look at the energy of those backscattered heliums. If you put in an energy-sensitive detector, you can actually deduce the mass of what you just scattered from. It's the classic two-body scattering problem. If you know the scattering energy and the scattering angle, you can deduce the mass of what you just hit. There are also photons that can come out. For some materials, you get a lot of photons. For some, you don't. A lot of these are the 22 eV photons that come up when helium de-excites. And there's also a whole cascade of other low-energy ones. And if you've got fluorescent nanoparticles or fluorescent proteins, there's an opportunity to excite those. This is work that we have not done a lot of development on because we don't have the expertise. But some of our first customers are studying this. There's also recoiled atoms. These are atoms that were part of your sample originally, can get knocked out. This is so-called sputters at low energy, a few eV. But there's also high energy ones. I think it's called MSRI, mass spectroscopy by recoiled ions. You can study the energy of these, know the energy of your primary beam, and deduce the mass of what you just knocked off, which is a terrific analytical capability that, again, we're not developing as part of the tool, but the physics is well-founded. There can be Auger electrons. A lot of people have told me you'll find very low rate, and I'm inclined to believe them. But there's occasionally someone who says, you know, there really ought to be some that would be very interesting. We don't have any data on it yet. We just want to do that measurement. X-rays, this is another one that's somewhat debated. There's actually two camps on this one. There's one camp that's absolutely sure we'll see some. There's another camp that says we're absolutely sure you won't see any. We actually did do a couple of experiments here. We know that they are produced, but at a fairly low rate. The mechanism is I think, what's primarily under debate at this point. And again, it's going to be our customers who figure this out, the people who buy the first instruments who want to do that research. So all of these different particles on the left-hand side can convey different informations about your sample. These are topographic or surface-specific information, elemental information, electrical properties such as a voltage contrast type information, magnetic properties, optical properties, crystalline information. All of these different informations get represented by these different particles in different ways. And there's a big matrix chart here indicating roughly how this information gets distributed. But we're developing new detectors, or in many cases in the field, new detectors are being developed in order to find better ways to exploit this information. Now here, onto some of the applications, some of the images. This is a fairly old image when we first got the tool working, but this showed us right away that we had something unique. This is a foraminifera from Woods Hole Oceanographic Institute, little dead skeletons of creatures that lived a long time ago, I guess. But what we found is we didn't have a charging problem. The helium beam interacts in a very different way than an electron beam. Primarily because as the helium beam hits, being quite greedy, the helium ion grabs an electron from the substrate right away and continues on the rest of its trajectory in a neutral state. So any charging that happens right at the surface. That's perfect for an electron flood gun. That can solve that problem quite easily. Compare that to a SEM where the electron beam goes in sometimes quite deep. In an insulator, that electron can't be just solved by a flood gun. It's very tricky to get out subsurface deposited charge. We have a unique advantage in that regard. This is a cell that we image, a white blood cell, and we're still looking at the biological applications, but the general observation is there's some of these biological samples that we don't damage nearly as much as the electron beam will damage them. And of course the contrast is different. Why you see these filaments here with a very different contrast, we don't know exactly. It could be material composition differences. This is an aluminum post on silicon. I showed you that image earlier. This is a comparison image. This is a semiconductor device with silicon on the surface, copper underneath, and a laser went in to mark a specific location. This is the secondary electron image, and it's nice by itself. You see an awful lot of topographic information. You can roughly tell the size and shape, but you don't know where the copper stops and where the silicon begins. But when we switch over to backscattered helium mode, I mentioned the cross-section of scattering of helium goes as the atomic number. So right away you can tell I'm looking at copper here and silicon here. You can now easily distinguish these different materials. So it's a nice, more or less orthogonal imaging mode that you can jump to quite easily. And you can even image simultaneously with these two different imaging modes. This is an example showing how we have terrific surface sensitivity. This is a single self-assembled monolayer on gold. So this monolayer was built up here and then patterned. They removed some of the atoms at the very end of it. And we were able to see that contrast difference of where it was patterned or where it wasn't. A very subtle difference in the top atomic layers. In an electron microscope, because you get that deeper penetration, you don't always get that surface contrast. This is a retinal tissue from a mammal. Again, the biological tissues we seem to damage a little bit less, showing a very nice contrast. These are collagen fibers. This is, just to give you a scale, this is 700 nanometer field of view. This bar is 100 nanometers. That's very high magnification. This actually came out of a mouse eye where they are doing some research in the fibers that make up the white of your eye versus the cornea of your eye. And there's these ringed bands here are very hard to see. And it also tends to charge very much. We were able to shoot these images without having to metal coat. We didn't have to hide the surface, and therefore we could now see these bands quite clearly and know that they're not an artifact of the preparation. This is an image of platinum, and you can see right away these are different grains of platinum, different crystallographic orientations. I'll explain that in a second. And this is a comparison SEM image, and you can see the grain contrast from one grain to the other. But you don't see the fine texture here. You can see little atomic terraces on these samples, which really shows you the kind of surface information that we can get. I wanted to explain just a little bit about the channeling. This is a nice example of a tungsten with many different crystal grains in many different directions. The channeling is just telling you as the ion beam enters. Oh, here's another picture of channeling. But if you look over here in this little animation, I'm going to launch a helium ion into this material that is not oriented parallel to the beam, and it bounces all around. It essentially gets lost, dissipates all of its energy fairly close to the surface, follows a lot of bounces. That would be a bright area in this crystal. But if we rotate that sample, so now it's parallel to the trajectory of the helium beam, you can see it can pass quite through quite elegantly. It goes through without producing a lot of damage. So that would be a darker region. So that's that channeling contrast that you can get with a helium ion beam, which is very interesting if you're studying very small grains. These are some dried and coated, I believe these were hamster ovary cells that came into our one customer's site that produced a really interesting contrast. And this is gold that's been patterned on top of silicon. This is a 1 micron field of view, so you can see there's really some very fine texture there. This is a 500 nanometer field of view. This is chrome on quartz, a typical semiconductor challenge. Again, not a charging problem for us, even at this very high magnification. These grains are on the order of 10 nanometers. But there's other imaging modes that we've started to explore. One of them is looking in transmission. There are transmission electron microscopes. We tried it with the helium beam. We made a very simple detector, a bright field and dark field. We got some very thinned out samples, and we looked at them. And what we found was there's some really unique contrast mechanisms in these very thin samples. There's a contrast mechanism in the bright field that's completely different from the dark field. And we can see a lot of really neat details that you can't always see. So that possibility is there. The future of it is up for grabs. Someone, no doubt, is going to explore this in a little bit more detail. We also, when we had that detector, we found something we weren't expecting at all. We and I have made the claims that wavelength isn't important. We're massive enough so the wavelength is quite small, small numbers of picometers. But we saw something that is a wavelength effect. We saw a diffraction type contrast mechanism. These are magnesium oxide crystals. This bar here is 20 nanometers, so it's very high magnification indeed. But you see these bands here. This is an interference effect. And indeed, you can have an interference when you pass through a crystal. We weren't expecting it at all. We had to bring David Joy on board to help us explain this. And I think in next month's Microscopy and Microanalysis, you'll find David Joy's explanation of this phenomena. Some people have also used this for patterning. So from here on in, I'll tell you about things that are not just imaging, but things you can do to your sample. This is a single layer graphene. This was done in Singapore, is that correct? Correct. National University of Singapore. And he used the helium beam with a patterning system to produce different dosages in different areas. And he was able to thin down this graphene to one single layer that is just 5 nanometers wide. Part of his field of research, not something we have expertise in, but I know here at Georgia Tech there's quite a lot of expertise in this field, and it might be of interest to you to see these kind of results. One of the other things, our collaborators who are right in our same neighborhood at MIT were interested in membrane folding, and they were using gallium to induce stress by breaking polymer bonds and such. And they wanted to put a beam down and see something bend. Well, it turned out we were terrific at that. And in fact, with gallium, it always points down. With helium, we can make it point up. If we use a high energy beam, 22 kV, we point up less. If it's a lower energy, lower energy, lower energy, lower energy. We can actually make it fold down. So he thought this was terrific and started making origami and paper cranes and all kinds of cool stuff. His actual interest was in making circuits that can fold upon themselves. But other people have wanted to make boxes out of these small membranes for encapsulating things or pharmaceuticals or other such applications. There's also patterning of resist. You can do lithography. Here's an example of some of our early work. We soon got on to finer work. And I think our most recent work, I can't remember if this is from the Netherlands or from MIT or Harvard. One of these institutions started doing lithography, and they're getting very nice small probe sizes or small pillar sizes. Some of them you can see knocked over here. I showed you just so you can get the aspect ratio of these. There's much less proximity effect. Again, imagine the helium beam entering the sample. It stays collimated as it goes through, and it doesn't backscatter a lot. So a lot of those things limit the performance of an electron beam. We have no trouble keeping it focused as it enters the sample. There's also beam-assisted deposition. So if you add a gas, flood it in, while you're rastering your beam, you can build something up. Or if you do the opposite, if you add a corrosive gas and pattern it with the beam, you can actually cause material to be removed in that area. Yes, helium will sputter by itself, but it's not the heaviest of the noble gases. It doesn't sputter a lot, so you can really exaggerate this effect with another gas. Here's something that we built up, these little nice cylinders. Here's something even taller, about 45 nanometers wide and 7.9 microns tall. That was made out of tungsten. And here's a hole that we bored. This is a hole around 300 nanometers deep and around 10 nanometers wide. I'm sure there's people out there who want to have holes of such narrow aspect ratio. I'm just going to go over very briefly because I want to leave enough time for questions at the end. I want to go over just briefly that there's this is probably the last part I'll cover. I mentioned that you can study the helium that bounces out. If you know the energy and you know the angle, you can deduce the mass of what you just hit. So for a fixed detector angle, if you know the backscatter energy up here, let's say this would be, say, 70% of its original energy, and you know that you are hitting, let's say, something of mass 12, it'll bounce off with just 32% of its original energy. So you'd be able to identify carbon. If you wanted to identify silicon, it's going to bounce off, the helium will bounce off with around 57% of its original energy. So this is a fairly simple way of deducing the mass of what you're imaging in a quantitative way. Now, it's a complicated scattering problem because you can scatter both at the surface or below the surface, so the interpretation of the spectrum is not trivial. But nonetheless, for thin film samples in particular, it's a neat way of doing metrology of that thin film. You can either identify what the composition is, or you can figure out how thick that sample is. This is a cartoon diagram of our backscatter detector, and that is now an option with the instrument. We've developed a solid-state backscatter option. And these are the different spectra you get with different bulk materials. And you can see they are easily discernible. Even copper and nickel, neighbors on the periodic table, are easily discernible. Here's a thin film that we were able to analyze, and we were actually able to do angstrom level thickness monitoring using that technique. So wrapping it up and leaving time for some questions, we developed this new source technology, which allows us to make this new type of microscope, the gas field ion microscope. I expect in the future there will be others trying to enter the market with these microscopes. Right now it's only a Zeiss product. Unlike a SEM, this beam is not adversely affected by diffraction or SE2s, so we can get sharper images for both of those reasons, sharper than a traditional SEM. Unlike a gallium fib, the sample is not rapidly destroyed by the beam. That's where the damage starts to come into play. The applications are varied and they're growing up. We're learning them as we come across. But basically, we can do imaging at high resolution with new contrast mechanisms. We can do compositional analysis. We can figure out what you're looking at. And we can do sample modification by either lithography or these beam chemistries that can add or subtract materials. So the instrument is more or less a general purpose jackknife at this point in time. And again, I think of it as an infant. It's a toddler. It's just learning what it's good at. We're spreading it out as much as possible to you, the people who have the imagination and have interesting, challenging problems that maybe cannot be met. And we're learning from you folks as what ideas you might have for this new technology. Thank you for your attention.
Questions? I have one.
Sure.
So for the elemental analysis using the backscattered helium, what's the spatial resolution? Maybe you said this.
The lateral resolution. Yeah, that is definitely limited. You're guessing it's limited because of it goes underneath and it can scatter some distance away.
Exactly.
Yeah, so that's one of the mechanisms that can certainly limit it. The helium ion beam will diverge. The helium atom goes underneath the surface and scatters out. So that would limit you to perhaps 10 or 20 nanometers. There's another effect which is quite similar. I mentioned we do sputter at a low rate, but we do sputter. So if I analyze too small an area, it will be gone by the time I'm done. Now that one's very geometry dependent. If I've got an infinite supply of it, I don't have to worry about it. If it's a thin film, I'm limited even more than that 10, 20 nanometers. If I've got a thin film, I have to worry about the fact that if I even blur the beam to 10 or 20 nanometers, I will sputter it away before I can get enough spectra. The fact that our backscattering rate is relatively low helps us in some regards, but it also hurts us in some other regards. That's one of the reasons that we think the elemental analysis by backscattered helium is valuable. But probably, and a lot of people have suggested, why don't we start sputtering material deliberately and enjoying the benefits of it? We could actually take those sputtered particles and now do some mass analysis of those, a SIMS type approach. And that's not something that we have in the product right now. There's a number of people who are interested in developing detectors that can perform in this regard, or at least find out what the promise would be in this technology.
So for the compositional analysis, like what's the mechanism you use? You're looking at X-ray or what kind of?
That was actually when we first developed the imaging technology, we realized that the traditional SEM owner can have a nice EDS detector that's quite efficient and quite evolved, and it works terrific. And we realized they'd be feeling a little left out if we didn't have some kind of compositional analysis capability. And there really is very little amount of X-rays produced. It's current belief is it's too slow to be of practical use. So the next best thing we could think of would be the backscattered helium, where we measure the energy and the angle. That's very much akin to RBS analysis, or what's sometimes called LEIS, low energy ion spectroscopy, or medium energy ion spectroscopy. It's very much akin to those techniques, and that's what we've developed, is that backscatter analysis. And in the future, the SIMS, I think, will probably gain some more traction, and I hope we offer such a technology in the future. How do they get ionized? Well, it's a little bit mysterious. Of course, you can't see what's really going on, but we have these cartoon pictures. And the cartoon picture, I'll just scribble on the whiteboard if I may. Let me do it on the front here. Okay. And this is just a cartoon. We're not exactly sure. But if these are the atoms of the emitter, here's the next shelf of them. So this is roughly the end form of the emitter. The electric field is large all around here. This is the area where the field is around 3.5 volts per angstrom electric field strength. So the helium that's wandering around here gets polarized, pulled in, and just not every time will it go in there and get ionized. It can actually bounce around several times until its energy gets less and less. And now if it's going slow enough as it passes through here, if it's going slow enough, the quantum mechanical tunneling possibility becomes appreciable. So now, as that helium enters this disk, the electron zips into the bulk material, causes no damage. And the remaining ion over here, the helium ion, is now positively charged near this tip, which is at 30 keV. So it takes off in this direction and ultimately will end up at 30 keV of energy. So it's really a quantum mechanical tunneling, ripping the electron out of the helium atom. We think of the helium atom quantum mechanically as being a bound state like this, where the electron's living happily at some energy level like this. In a high electric field, it's more like this. So now that electron can either spill out or be on the verge of quantum mechanically tunneling out. It's not fully understood. There are a number of scientists who've thought about this for a long time. They're perfectly happy with the model. It seems to agree with all the experimental data, but it's just our best guess right now.
What's lifetime for the chip? In some way that's maybe atom lock out or just get the clogging, that's the helium absorption.
Yeah, there can be a lifetime to the tip, and that was one of the barriers we had to cross before we became commercially viable. We had to be able to get that tip from a rounded shape like this to this faceted shape like this, where we have a single apex at the end form, and be able to go back and forth. So we had to develop that in situ. So those atoms that are very much at the apex, they may last only for a week. That atom will actually pop off in time. It's almost unavoidable. The lifetime is typically from 3 days to sometimes 3 weeks. A single atom will stay there. Once it pops off, we have to do a reforming. And all of that surface science that tells people how to induce faceting, we do that automatically in the instrument. So it's a UHV system. We don't actually have to open it up in order to go from here to here and back. Thank goodness. So you can do that, and it takes maybe a half hour to reshape the tip, and you can operate for 3 to 10 days with that single atom at the tip. There is a lifetime as to how long you can repeat that process. We believe it's around 50 times. We've certainly had cases where we test them in the lab, 50 consecutive builds in a row. If they typically last a week, that's a year's worth of rebuilding. When the instrument's in the field, I think we typically say there's a 6-month expected lifetime to the tip before we replace it. But in practice, it gets replaced because of some other reason. They want to do an experiment, for example. So it's not uncommon to have 6 months to a year as a typical lifetime of an emitter.
So how you show that you form the apex or just the arc shape?
I'm sorry, what shape is?
How do you know that it's already got the perfect apex shape?
Well, when we that's right. If it was in a field ion microscope, you just look at that emission pattern hitting a phosphor. We've essentially built into our microscope a special mode where we can look at that whole imaging pattern. So, for example, if this is a well-built-up tip, you'll just see those 3 beams coming down, 1, 2, and there'll be another one here in the back. And you'll have that hit a screen, and you can look at that pattern. If it was in this shape, you'll see hundreds of little beamlets. So built into the microscope is a mode where you can examine the quality of the emitter. And we put it, effectively, it's like putting a screen here, seeing the pattern, and then you make a visual impression of, yep, I've still got my single atom at the apex. I'm going to keep on imaging. Or if you see some hundreds and hundreds of atoms, you go through this process that happens in half hour to an hour. And then you're back with just 3 atoms at the tip.
So John, is the ion beam pure? Do you get only helium plus, or do you get also singly charged dimers or doubly charged monomers?
We believe it's a singly charged helium. We're very confident of that. But I would say it's not perfectly pure. There can also be neutrals that come down. And the mechanism there is you create a helium ion up here, but it can have a close encounter with another gas atom, and it could steal his electron. So it's going to continue on. Even though it's aiming at going on at 30 keV, it can get neutralized, and it goes on at 30 keV. Fortunately, those ones don't get focused or scanned, so they don't add anything meaningful to the images. But there are some neutrals, typically a very small percent, but unfocused. There's also multiple isotopes. You can, I happen to know, order just helium-3 gas of very high purity. The same thing with other noble gases. You can get very high purities of a single isotope if you want. So in principle, with your garden variety helium, you will get both helium-3 and helium-4 in your beam. Fortunately, they behave the same. They focus and scan exactly the same.
If I may ask another question, and all your work is in ultra-high vacuum. I know you probably have never thought about doing this, but can you work at reduced pressure? Could you do your ion beam generation at high vacuum, but then the last stage do this, let's say.
So instead of an eSIM, eSEM, make it an eSIM. So have an environmental chamber down at the bottom of the instrument. Could be done. We have not pursued that. It sounds very interesting because there's an awful lot of things you can do with an eSEM. We have not pursued that. There's another question over here.
Yeah, you mentioned imaging the various kind of the polycrystallinity of the films in the dark areas. Is there a way kind of akin to XRD of actually being able to definitively determine the crystal structure of this dark area here?
Yeah.
Light one here,
Yeah, actually, it's very interesting. There's you may be familiar with the electron beam version where you do, I think it's called EBSD, where you have an electron beam come in, hit a crystal, it has a very interesting diffraction pattern, and you look at a phosphor screen nearby, it recognizes the pattern. A computer system does. I think Bruker and Oxford make these kind of instruments. And you look at that pattern, and a computer says, oh, I can tell you exactly the orientation of that grain. Now, in principle, the same could happen with an ion beam, but there's technical challenges to doing it with an ion beam. The physics may be a little bit different because it's less of a wavelength phenomena and more of a blocking phenomena. But still, in principle, there's a blocking pattern that you could see. Helium beam comes in, hits a grain, and the pattern will tell you what that orientation of that grain was. This is the kind of speculative stuff that it's really terrific to hear these different ideas, because it's very often it's not stuff that we'd ever think of, or we wouldn't appreciate that there's a value in it. But we've got to get all these things ironed out and figure out, do you see a useful pattern? Could that be of commercial value to someone else? We don't know. We'd have to try it.
We don't have an ultra-high vacuum chamber, though. The chamber...
I'm sorry, the chamber is, I should clarify that, we typically get as clean as we can in our sample chamber, because contamination is very critical if you've got a real surface imaging instrument, and that's what we've got. So we found out how to clean everything and keep our vacuum cleaner than any SEM has ever been for sample area. Up in the gun area, it is ultra-high vacuum. In the sample chamber, it's typically in the 7 scale, so pretty good vacuum in the chamber. Up in the gun area, it's cryogenic. It might well be in the 10 to the minus 10 torr range. We don't have a gauge up there, but certainly when you've got a cryogenic surface up there, there's terrific pumping speed.
Is there a different chamber for the biological samples, or is this all the same 10 to the minus 7 vacuum?
It's all in the 10 to the minus 7 torr. When we put in a biological sample, it probably degrades. And we have taken a number of steps. We're really just learning on the biological samples about how to properly prepare them. Invariably, there'll be some challenges. One of the early thoughts is maybe we want to have a cryostage. That can certainly prevent any of the outgassing that's associated with organic chemistries. So that will probably be coming on either at one customer site, or it may be offered as a Zeiss option in the future. Yes?
Can one change the temperature in their ultra-high vacuum chamber?
The sample's temperature? We've only done experiments. As a commercial product, we don't. But we found it very curious, our curious people back in the factory. We found a way to heat the sample, and that was really terrific in outgassing and removing that adsorbed layer of stuff. And we've also tried cooling it. That helps a lot in terms of reducing the mobility of the hydrocarbons that are on the surface. So we did some rough experimentation. It's not part of the product. I believe Protochips is a company that has this heated sample holder that looks really exciting, where you can actually heat it up to 1,000 degrees in a matter of a second or so. So if you want to see evolution of crystals or catalytic processes, you can study them in situ, which sounds very exciting. We haven't incorporated that into our product, but I've talked to the Protochips representatives, and they think that this is a natural fit.
Anything else? All right, let's thank John again.
Thank you.